Okay, arrange these compounds from strongest to weakest base. So first what we want to look for, so we should know some pKa's, right? The pKa of a protonated amine is approximately 10. 10. And so that pKa table, when you add these substituents on a benzene, right? So if you go benzene with R, or with NH3 plus, it generally moves the pKa down 5, right? So, for example, right, we know our pKa table: 0, 5, 10. Hopefully you have this, you know this. Approximately 15, 5. Guys that are less than 0. So H3O plus, protonated alcohol. Trying to run through these real quick. Make sure you know them. Protonated carboxylic acid. Right. O, H. Hopefully, sorry if you can't see that. I guess plus. Right. So that's around 0. Around 5 is regular carboxylic acid. OH. Around 10 is our protonated amines, right? So that you should know that number. Around 15 is H2O and ROH, right? So the idea is if I add a benzene to an alcohol, it drops it by 5, right? So it makes the pKa approximately 10. If I add a benzene to a carboxylic acid, in my mind it goes to 0. I kind of remember that from the course. That's the way I think about it, right? You know, adding the benzene to these groups decreases the pKa, makes it a stronger acid, right? And so stronger acid means weaker conjugate base. Weaker acid means stronger conjugate base. I'm just going to erase these tables. I need some room. So basically, we know this guy's going to be around this. Let's see, this conjugate acid is the weakest. Says the strongest base is going to be 3. Right? And so these guys, now we got to compare these two guys. We know they're both going to be weaker bases than this guy, but we got to compare them to each other. And how we're going to do that is by looking at the substituents, right? And so these are with benzene rings. We got to know activating and deactivating substituents. So we know this is a deactivating substituent, so it's going to pull electron density away from the benzene ring, which will, let's see, that the more electron density that's pulled away from the benzene ring, when this guy is straight across from it, that will increase the acidity, which aka decreases the basicity, right? And this guy is slightly activating, okay? So activating substituents will add electron density to the ring, to the group straight across from it, which will make it more basic, less acidic, right? Because it will add minus charge to the conjugate base of the acid. So it makes the conjugate base less stable, right? So we can show this through resonance, because you might not be able to memorize these guys. So if we do resonance, let's see, this guy is O, let's just get rid of this. Minus charge here, plus charge here. So we can go boom, put a minus charge there, and pull some electron density out of the ring and donate this. What does it do? It makes, if I push the electrons in that way, the resulting structure is NO minus minus. Let's see, we still got a plus here. We went down here, here, double bond here, N, H2. So we gave this a positive charge in the resonance. And we're talking about this is a conjugate base. or just a base. So can we pick up a proton with a positive charge? No, that's going to be a very weak base. So this guy, this is not going to be able to donate any electrons or withdraw any electrons from the ring due to resonance because this is an sp3 carbon. But what it does is, so these are slightly nonpolar bonds. Let's see, you have electron density there. It does by, I think you call it inductive electron donation. The idea is this is more electronegative, this ring is more electronegative than the methyl, right? So it just pulls a little electron density to itself, right? Putting electron density closer to the end, making a little more negative charge here, which we're trying to pick up a proton. So a little partial negative charge will help us pick up a proton, making it a little more acidic. Yeah, which stabilizes the base, right? So this was an unstable base. So it's a weaker acid, that's what I should say, right? No, this is a stronger acid. This guy's more stable. Well, this guy said it can't go back. Okay. This guy's less stable because it's more likely to pick up a proton and go back to the acidic form, right? So for equilibrium, A minus plus H plus, right? So this guy more likely to pick up this H plus and go back over here, increasing the amount of base in solution. So it's a stronger base, stronger acid. So basically we go, right, we already said this was strongest, 3, 2, 1, backwards order. Oops, should be D as our answer. Strongest acid there, yeah. Okay. Strongest conjugate acid there.